As long as we're working on the counter shaft for the Mega, I thought, and I have the Ultra, the fat motor drives right up here on the bench also. I thought it'd be kind of fun to make a comparison of the two. On the right, of course, is the Ultra, and the counter shaft is that piece on the bottom with the big pulley, small pulley, and does the same function as the counter shaft on the Mega, although it's much larger and is much wider in belt, and it's also 8mm rather than 5mm. Okay, what we have here is the most used intern on the planet. This is my prototype. It runs pretty much every day, sometimes overnight. Hundreds, if not maybe even thousands of hours on it. It's a couple of years old. It's going to be replaced now by the Ultra, and this is sold. So prior to delivering it, I'm going to go through the machine and do all of the upgrades that have happened over the last 2 years, so that the customer gets the machine that's current. What I want to show in this video is the counter shaft and the differences between the Mega, which is this, and the Ultra. The Mega counter shaft is one of the things that got upgraded because my prototype machine has been called on to do things that we were never designed to do. It's far beyond its actual capabilities, and it constitutes abuse, but that's pretty much what I'm known for. The only failure on the machine, even turning 98-pound spindles for the Ultra, was the front bearing on this counter shaft. The complication comes when you design a part with this size bearing, and then you find out that you can't get this size bearing in a high quality name brand bearing that you want to use. The counter shaft for the intern Mega is significantly smaller than this, and this is 8mm pitch belt, and this Mega's only a 5mm pitch belt, so it's probably about half of the size. But in order to be able to handle the 5 horsepower, which is what the Ultra is designed for, and that limitation is primarily with the belts. Also, when you run a belt around a pulley like this, the smaller the pulley is, the less horsepower you can run through it. So a lot of factors come into play when you're figuring out how much power you can run through the mechanism. This guy is a hardened steel pin, and this is steel. So this guy is very, very rigid mount. And then by putting the bearings inside of the pulleys here, we actually can put a much higher load rating. These are precision rollers in there. It's a needle roller, but it's in a machine hardened case rather than the typical sheet metal cup that they put these in. So these kind of roller bearings, needle rollers, need to have seals in them, and there's 2 of them in here. So they're pressed in. Here's the piece. This is for the 5 horsepower guy. This is for the 2 horsepower. These use the narrower belts. So, but it's the same part. It's this piece. This is new. This hasn't been blackened yet. So the aluminum pulley then gets pressed onto this shoulder and locked up. So then inside of this go these needle rollers. So a needle roller like that gets pressed into here. It's not a big press fit. It's about 1/1000 of an inch. So it'll keep it in there, keep it from wandering around. So, and it's got a little oiler hole right here, and then it's also got this groove that's around the outside is to distribute grease, but I kind of use it for a different purpose. These little set screws that are in here, this is pressed in, and the way you press that is you make a washer of the right thickness, so that when you press this down, it'll press in until the washer hits. So you get that exactly right. Now this, you see where this groove is aligned with that set screw, that's not an accident. So the set screw will go in and it'll reach into this groove just as a precaution, so that in the event, an very unlikely event that press fit loosens up over time, then the set screw will keep this from wandering around. So this is what this part looks like. And that reaches all the way through there. The first design I had was I had there was a bearing in the pulley, in the big pulley, and another bearing in the small pulley, and they were just pressed together right here, very very small amount. And I had a sealed ball bearing in the back. It's much bigger. So a sealed ball bearing in the back on this gear, and then the rollers, the needle rollers on this, because there's not enough room for a ball bearing in this arrangement. So, but in my mind, I could just see these two pulleys rocking and over time loosening up. So I just really didn't like the idea of having an insecure connection between these two. So the solution to that was to take this, I'm going to call it the pinion pulley, and run it all the way through. So that's one solid piece of steel. It can't disassociate from itself, and it's not going to start rocking or come loose. It's one solid piece. And both needle rollers are pressed into this. So you got the back needle roller is still for the big pulley, but it comes through this case right here. So in order to do torque transfer, now there's set screws that go right through this pulley, and if you put set screws in the pulley, make sure you put them at the bottom of the tooth, because that way they don't tear up the belt. If they're at the top, it's not as good. When we're talking about almost 5 horsepower, and 5 horsepower is pulling this outside belt, and then the torque multiplication is going down to this. So there's not really enough friction in 2 set screws. So this is an interesting trick you can do. In lieu of putting in a keyway, you can drill halfway between. Now this is a steel and aluminum, but it's 70-75 aluminum, and it's 12L14. So in other words, it's soft steel and hard aluminum, so they're not that far off. Otherwise, it gets more difficult to do this kind of thing. But you can drill halfway in between, and this is 3/4 of an inch deep, and then you tap that and you put in this is a set screw. So that's what's going to transfer the torque. We're not going to rely on those little set screws. So this goes right on this guy, and this there's going to be a seal in the back. So let's look at what we got in the way of a seal for the back of this thing. So there's the seal for the back. So we might as well go ahead and stick that in there and put some grease in this sucker, because it's going to go. This is going together for the last time. So we have that the back seal, and then we need some way to, because these needle rollers, they don't locate themselves laterally on the shaft. So we need some way to keep this thing from wandering this way. So the way to do that is you can put a thrust bearing on either side, but that becomes awkward to disassemble it if you ever need to. So the way this works is there's going to be thrust bearings, and these are the thrust bearings. And then it involves a little washer, and then the needle thrust, and then another washer, and that's your first thrust bearing. So that takes the thrust in this direction. It keeps this from walking off that way. So we also need to keep it from walking back too far. So we need a second thrust bearing, and rather than put them front to back, which the back one starts to cause a problem with the seal and so forth, we're going to put them both in the front. And the way that happens is we have a snap ring here on the shaft. So that snap ring is going to be sandwiched between two needle roller thrust sets, and they can't go in either direction. And there's an internal snap ring that goes inside of this barrel. So to put this thing together, I have a drawing over here that I don't usually disclose in the drawings, but it's kind of hard to see what's going on inside of this thing. So I'm going to break with tradition a little bit. Now this was really pretty at one time, but it's not so pretty anymore, but it still gets the idea across. I don't know if the camera's going to see this or not, but hopefully it will. This is the piece, and it's arranged. Oops, it's arranged this way. So what we have in the back, we have a grease seal, and then we have a bearing, needle roller bearing, and then in front of the needle roller bearing we have a wave washer. What the wave washer does is it keeps the pressure on without being too tight. It won't bind anything up, but it'll keep pressure so that this thing isn't fluctuating back and forth and making knocking noises and so forth. The next thing is the needle thrust, and then there's a snap ring on the shaft itself. Now there's another needle thrust, and then there's an outside snap ring, which is on the inside of here, and then finally another grease seal. So that's how the thing is arranged. So we're going to put this thing all together. So the first thing I want to do is, so if you wanted to put a Zerk fitting or grease fitting that would, like you could put one right in here, you would go through here, you could actually take, you wouldn't be able to leave the fitting there, but you could screw a fitting in, grease it, take the fitting out, and put a plug in if you needed to. We're gonna take the attitude that this is lubricated for life. So we're gonna put enough grease in there that this thing is gonna run for 20 years and not need any more grease. So we're gonna get plenty of it in there. But this whole idea of packing, the grease so that there's not 4 molecules of space in there, really not a good idea, because what will happen is as it heats up, all it's going to do is force that grease right out of the seals. And in some cases, it'll push the seal out with it. So we need enough that as a lifetime supply, this stuff will actually heat up and move around in there. So it's, I think that's good. Mobile 1 synthetic. Pretty good stuff. So, you get this grease on the back. So, this is only a little 1/8 inch grease seal. We want it to be flush with the surface. Here, you pull it. So that should be flush. So we're good to go there. So let's get this on here. Start putting cool stuff in the top of it. All right, so the first thing that goes in is a wave washer. These guys, they put a little bit of this typical bearing stuff. This is it's just a little piece of spring steel, and it'll impart. So you put it in there, you smash it between 2 flat surfaces, and it'll impart a little bit of spring. So we're going to put that right in there on top of that needle roller. And then when this washer goes on there, it'll press against the washer and keep all of these thrust bearings tight. All right, that'll find its way around. All right, so now we got that in there. The next thing that goes is a snap ring on the shaft. So, and the snap ring on the shaft is going to press against that needle thrust and compress that. So let's stick this guy in there. So this is what we got so far. We're getting some resistance now because of ulcers and so forth. All right, so now on top of that, we have another washer because we can't run this against that snap ring. Last washer. Again, I'm going to stick my fingers in this stuff. And that'll find its way around there fine. So, now we need to get this big snap ring inside of there. If we push this down, hopefully we can see that groove. The problem is I have to compress this against that wave washer that's in there. And what I have is I got the pin mount is on the bench and I'm pressing against that so it doesn't snap in. There we go. Alright, so that happens to work out. So there's my seal for this side. So here again we want to tear up that seal lip. So we'll put a little bit of that grease on that seal lip so that it will pop on there. Okay, we're back. We're going to put together the fat motor drive on the intern Ultra. This is the top plate for the intern Ultra. And this is a lifting ring. And there's some, on this prototype, there's some clearances machined in on the inside. And the production unit's just got a little bit taller frame so that this was unnecessary. But you really want to, you don't want to just go crazy and make this thing tall because it has to fit under the mill head. So excess height is not a good thing. So typically what you would do to lift the intern, and this particular one with the fat motor and the fat motor drive, just the intern and the fat motor drive is 140 pounds. So we really don't want to be trying to carry that around low. Now most of these go on an outrigger plate, so the outrigger plate would space it up, and plus it's hanging off the edge of the mill table. So this loop right here that comes down actually falls below the level. So I'm going to put the fat motor in this first. Let's see if I can get this out of the way so you can actually see what's happening. Alright, pull this guy over. And this way. Okie dokie. The reason for the ultra heavy top on this is because of the fat motor drive as part of the motor mount. So really, so lift this guy up, our eccentric in, put him back down, put the bolts back in.